This is the energy required to rip an electron from an atom. If that atom loses an electron, what happens to the atom? And one answer was it loses an electron. I already told you that. Come up with a new answer. Let's pick hydrogen. Hydrogen comes in with a proton, an electron. That's it. I rip an electron away. What's left? A proton. So the charge on that atom becomes positive. Ionization energy is always referring to the atom becoming positive. Every single time. Right? Since we're removing the outermost electron, depending on where that electron is located, if we think back to radius, can help us predict something about the energy necessary to rip it away. Okay? There are some trends. Whoops. There they go. Okay. The ionization energy generally increases as we go from bottom to top, and it generally increases as you go from left to right. Okay? Which roughly mimics radius. Okay? The smaller the atom, the higher the ionization energy. The further up we are, the higher the ionization energy. The further to the right we are, the higher the ionization energy. That matches roughly with our radius. The issue here is that it says in general. What does in general mean? Usually. What does usually mean? Exceptions. So everybody goes, oh, there's exceptions to this. There are absolutely no exceptions to what is actually happening with ionization energy. This is not what is actually happening with ionization energy. Okay. What this is a kind of hand-wavy makeup. I see a trend, so I'm going to memorize the trend, and then I don't have to think about what is actually happening. Okay. I then have to memorize the trend and the exceptions, and then I don't have to think anymore. Okay. That is excellent if you don't need to think. Okay. You are being trained to think. Okay. That is what we're trying to get out of all of your education, is getting you to think. If it was just regurgitate a bunch of facts, that's pretty useless. Right? So what is happening? Wow, this is going really slow. Right? So if we go through and take a look at what's happening in here, notice that as we move, we start with hydrogen, so our atomic number. Start with hydrogen, and I add an atomic number, what happens to the ionization energy? It goes up. That made sense. Left to right, it increased. Okay. I then go to lithium. So I compare hydrogen to lithium because they're in the same family. The ionization energy drops. Why? Lithium was bigger than hydrogen. The outermost electron went into a higher energy level. It's closer to being ripped away from the atom. Okay? As we move left to right, what happens? It increases again. So as a general trend, it increases, except there's this weird drop, and there's a second weird drop. And if we notice, that weird drop is pretty consistent through each of those trends, or each of those systems. Okay? Well, if it's consistent, there's probably a reason behind it. So let's address that reason. All this is coming to is where the electrons are located. Okay, so let's pick our first trend. Right in here. What elements are we looking at for that quote-unquote exception? We'll call it the red element and the blue element. Which element is red? Which element is blue? Beryllium is red. Which element is blue? Boron. So I want to look at the electron configuration for beryllium. Before I ionize it, what is the electron configuration for beryllium? So where are all of the electrons for beryllium? First one is where? You're like, what? We didn't talk about it. Yes, we did. 1s, 2, 2s, 1, right? Or sorry, 2. How do we know it's 2s2? Where's beryllium on the periodic table? Second column and second row. Second row, 2. Second column, 2. Okay? That's what those mean. How do we know it was S? S is a sphere. And I don't mean to call you out for this, but today is Tuesday. Like, how is that relevant? Exactly. The sphere is neat. It is a sphere, but just like today is Tuesday, that's not relevant to why that says S.
It's the first shell.
I'll kind of go to that. It's not officially our first shell. It's in the S block. Remember the sections of our periodic table. Okay? That's how we know that is S. Okay? What would its configuration be if I removed an electron? So what electron would I remove? I've got 4 to choose from. I'll move one of the 2 S's. I'll remove the highest energy one. So 1s2, 2s1, because I removed an electron. Okay? What does lithium look like? That's not what I wanted to ask. What did I want to ask? Boron. What does boron look like? What is its electron configuration? 1s2, 2s2, 2p1. Remove an electron. What does it become? 1s2, 2s2. Right? Okay. Do we do that whole close your eyes and envision the pretty people?
Yeah.
Yeah. So we know symmetry is important. The more symmetric something is, the more pretty it is. Okay? So let's take a look at beryllium, where it started. Everything is entirely full. Is that symmetric? Yeah, if everything's entirely full, that's pretty symmetric. Right? So that would be roughly equivalent to saying that is beautiful. Did I spell that right? B-E-A-U-T-Y? Yeah, okay. Beauty. What happened when I removed an electron? It's not symmetric. So when I remove an electron, what does it become? Okay, this is the beauty and the beast theory. Okay. Someone comes along, says, you are beautiful. I'm going to hit you with this stick, and you're going to become beastly. Are you just going to accept that? Why not?
I don't want to be ugly.
You don't want to be ugly. Let's go with beast. Beast is a little bit less, you know. Right? I do not want to become beastly. You are going to fight back. You are going to prevent that from happening. Meaning you're going to add energy in to say, nope, don't do that to me. So what happens to the ionization energy for beryllium? It goes up. It goes up higher than we might expect because we're transitioning from beauty to the beast. That's not so nice. What happens with the boron? 1s2, 2s2, 2p1. Is that symmetric? No. Okay, remember, there's 3 p orbitals. Only one of them has half an electron, or has 1 electron in, is half filled. Is that symmetric? I got 2 full, 1 half filled. That's not very symmetric. So that one would be best described as a beast. What happens when I ionize it? It is now symmetric, so it is now. Same thing happens. Someone walks down the street, sorry, these people aren't very nice. Okay? Says, you are a beast! And not in a nice way. Okay? Because you could be a beast in a nice way, right? Okay? You are a beast. I've got this stick. I'm going to hit you with this stick a whole bunch and you will become beautiful. You're now going to be like, oh, okay. I mean, it probably hurts. But at the end of that, I become beautiful. We'll probably accept that. So what happens to boron's ionization energy? It's still going to require some energy because I don't want to get hit by a stick. But if I get hit by that stick, I become beautiful. So I'll accept it conditionally. And so boron's energy goes down. The result is that we see an exception. There's no exception. It's Beauty and the Beast. That's all that's happening here. Right? Symmetry comes in and plays a very important role, but only when it aligns perfectly with our orbitals and the electron configurations. Where does it happen to align perfectly? Well, the transition between beryllium and boron, okay, which happens to be the transition between the s orbitals to the p orbitals. We see a big transition there. Okay? That transition is where we're going to see that symmetry pop up. Notice it happens in other stages. We also see it for oxygen and nitrogen. Why would nitrogen's energy be slightly higher than oxygen's? Well, it's the same theory. Nitrogen started beautiful. If I ionize it, it turns beastly. Doesn't like that. Okay? That transition is a much harder transition to evaluate because that transition is happening in the middle of the p block. It's not a different orbital type. Okay? So why might that be the case? Why is that happening there? Well, how many p orbitals are there? 3. Where is this exception between nitrogen and oxygen happening? In the transition between the third column and the fourth. You mean the transition where I'm all half filled? Yeah, they're half filled, but at least they're evenly half filled, symmetric, to all but one is half filled. Yeah, if you have a hard time doing it with your hand, it's probably because it's unsymmetric. Right? So we can look at the orbitals to predict something about those weird exceptions. Is that challenging? Absolutely. Are you responsible for understanding that? Absolutely. Do you need to be able to do that to pass this class? No. What are you responsible for passing the class? What is the trend? Okay? That's ultimately what you're responsible for. Okay? But maybe I think that's an important enough thing that I should include a question on the exam about that. Maybe. Okay? I think there's at least 2 people, well actually all I really know is at least one person that knows that to be true. Because what has that one person done? They opened up the practice exam, and when they read through the practice exam, they noticed that there isn't a question exactly about this concept as extra credit. Okay? Your textbook doesn't mention this, so don't panic, don't write down notes on this. There's this other concept of electron affinity. Electron affinity is the opposite of ionization energy. Okay? This is the energy required when I grab an electron from the vacuum and I pull it into the atom. Well, what happened to the atom then? Gained an electron. It is now more negative. Okay? So we can go through and do the same thing and evaluate something about or look at its energies and all that. And we can look at trends, yada, yada, yada. Not a big deal. The big deal is that if I combine the concept of ionization energy with electron affinity, right, what I'm now looking at is the ability, or kind of an average for the ability of an atom to either give up an electron or accept an electron. That is electronegativity. There's a few different ways in which the numerical values for electronegativity are determined. One is literally to take an average of the ionization energy and the electron affinity. Okay? Is electronegativity insanely important? Yes. It's what tells us what our bonds are, okay? What type of bond we have. It tells us where the electrons spend most of their time. So if the electrons spend most of their time on one atom over another, that atom starts to become negatively charged. Okay? Charge is an inherently dangerous and bad thing. I can now predict that that atom is going to interact with other positively charged atoms to neutralize that charge. Okay? That all comes back to knowing my electronegativities. Okay? So electronegativity is a measure of the ability for an atom to take bonding electrons from another atom. Right? When we go through and look at this, fluorine is the most electronegative, and then cesium is the least. Notice that they've got that entire bottom row with nothing written there. Why do they have nothing written there? And for that matter, all of the noble gases? The noble gases don't react with anything, which means they never form a bond, which means I shouldn't be looking at electronegativity, because electronegativity is measuring bonding energy. Okay? The bottom ones, though, could theoretically react. They're in the same family as everything above it, and those have electronegativities. Why is the bottom row not shown? Might help if we take a look at our periodic table on the wall. Most of that bottom row is what? Man-made, which means how much of it do we have? Okay. The other ones, we have like thousands of kilograms, tons, lots and lots and lots. The bottom ones, we probably have 2. Well, 2 kilograms, that's a size one. No, 2 atoms. Okay. Singular. We don't have a lot for those. If we don't have a lot for those, can we see how they interact with something else? No. If we can't see how they interact with something else, we can't predict or provide a numerical relationship for how they react with something else, because they don't exist long enough to react with something else. We can't make that observation. Right? So what you need to get out of this is the general trends behind electronegativity. It is opposite the trend for metallic character. Your most metallic is the lower left. Your least metallic is the upper right. Meaning the upper right is the most electronegative, fluorine. The lower left is the least electronegative. Okay? For those of you that are careful and look through it, you will find exceptions. Don't stress on the exceptions. Focus on the general trend. The 3 most electronegative, fluorine, oxygen, nitrogen. Okay? Those become important at a later stage, okay, for the sake of this class, but if you're in, anybody in a biology class? Yeah. What interaction, when they're talking about how molecules talk to each other, do they reference? Do they reference that? Bio class? Begins with an H. Hydrogen bonding? Does that ring any bells? Yeah. When do you have hydrogen bonding? When there's a hydrogen bound to fluorine, oxygen, or nitrogen. Why those 3? That generates the largest partial charge difference. That partial charge gets canceled out in a very strong interaction that we call hydrogen bonding, which, by the way, is not a bond. Right? So we can use electronegativity to come up with predictions about these things. Biologists tend to just memorize and say, this is the answer. Duh. Okay? Unfortunately, that's never true. Chemists do the same thing. Okay? Because then a physicist comes along and says, no, you're full of crap. It's actually this. Okay? And then the mathematicians do the same thing to the physicists. So everybody hates the mathematicians. Okay? I don't know why it happened here. Oh, I do know why. Chapter 4 summary. Those are all the things that you should know out of Chapter 4. Okay? Notice our electron configurations come into play here. The electron configurations give us something about predictions of radius and ionization energy. So if you don't know any of those pieces, you potentially ruin your ability on other things. Okay? Those of you frantically copying this down, by God, it's on the slides on Canvas. Okay? So you find a copy, that's okay, but remember, it's already, you have it. You literally have it. Okay? I made you feel bad. Well, you should feel bad. No, you shouldn't. It's okay. Writing can help you remember, as long as you're thinking about what you're writing. Okay? The only one that I would say is a bit kind of odd in there is through the middle there. I say Bohr was a discreet gentleman. Because discrete has like 2 definitions, right? Okay. What we're referencing as Bohr as being a discrete gentleman is because he defined our electron orbitals, because our orbitals were discrete energy levels. Yeah. Sometimes I'm clever. It's rare, but sometimes. Chapter 5, we get Mendeleev with the periodic table, and the biggest part of that is the ability to predict the properties of other elements. Okay? That's huge. The trends. We've got electron orbitals. Where are the blocks? Okay? Chemical and physical properties. That's ultimately our predictions from Mendeleev. Atomic radius, ionization energy. And ionic charges is one that's kind of floating in there that we will look at here in just a second. Okay? Wish I probably... will we look at ionic charges? Let's just say temporarily no. We won't worry about ionic charges. Okay? So there's our electronegativity again. Should be a good review because we saw that already, now multiple times. We have types of bonds. At this stage, we're really only classifying according to ionic bonds and covalent bonds. So we need to be able to look at a structure or a bond and classify it as an ionic bond or a covalent bond. If we can't do that classification, then the entire chapter 6, which is your homework after the exam, you can't do. Okay, you are actually physically impossible to do naming if you can't differentiate ionic and covalent bonds. Your ionic bond is defined as a metal and a nonmetal. How do you know it's a metal? You mean that stuff that Mike talked about early on, where we're like, oh, I knew that already, that was easy, I didn't have to worry about that? Comes back and bites me? Yes. How do you know it's a metal? Left of the staircase. How do you know it's a nonmetal? The right of the staircase. So using the periodic table can help you identify your bonds. Okay? Your covalent bonds are by definition going to be two nonmetals. Are we missing some? What happens with the semimetals? Don't worry about it. What happens with, I take two metals?
Polar.
That's not on here either. That's because that's a metallic bond. We also don't worry about it. Okay? Are all of our nonmetal covalent bonds going to be the same? Well, if I take a look at H2O, that's hydrogen, metal or nonmetal? You're saying a nonmetal, but isn't it to the left of the staircase? Hydrogen's a tricky element. Okay? There was a suggestion made earlier in this class by you guys that we should pull hydrogen and helium kind of off the table a little bit because they're its own, their own separate class, kind of. Okay? Hydrogen is sometimes shown on both the left and right-hand side of the periodic table. Okay? Because it can act as a metal and it can act as a nonmetal in some certain circumstances, particularly when it comes to its electron configuration. Okay? It is a nonmetal. So if I take hydrogen, a nonmetal, and oxygen, a nonmetal, I would then have a covalent bond. If I take hydrogen, a nonmetal, and chlorine, a chlorine's on the right of the staircase, that would make it a nonmetal. Both of those are nonmetal covalent bonds. Would we expect all covalent bonds to act the same? I take a beaker full of H2O and I throw it at you. Like, thanks for getting me wet. Throw a beaker of HCl at you and it's a lawsuit. That's a slightly different response for the exact same bond. Why? The elements change the chemistry of the bond. Okay? So we would have to evaluate beyond just those classifications to see those differences. Okay? There's some level of reactivity associated with those. So it's not as simple as just it's covalent or it's ionic. Okay? You aren't there yet, but I want you to be thinking about identifying those differences. Okay? Our ionic metals, or our ionic bonds, a metal and a nonmetal. The metal will always carry a positive charge. The nonmetal will always carry a negative charge. And that's because there's a full transfer of electrons between the two atoms. Okay? Why would there be a full transfer of electrons? Well, if I take sodium and I bond it to chlorine, sodium is a metal, chlorine is a nonmetal. Why would the electrons in that bond spend all of their time on the chlorine? I'll give you 3, 2, 1. Change your wording a little bit. It's not negative. Whoops. Where's chlorine? Chlorine has an electronegativity of 3. Sodium has an electronegativity of, it's really hard to see there, but 0.9. The difference in electronegativity there is massive. That difference is so large that when I put sodium next to the chlorine, the sodium says, take it, I don't want it. Get rid of my electron. It is the difference in electronegativity that actually is what's dictating the type of bond we have, not this metal and nonmetal. So when we look at sodium and chlorine, sodium's electronegativity is so low that it gives up its electron to the nonmetal. If it loses an electron, what charge does it become? Positive. We're now addressing something about the charges of these elements. Right? What happens to the chlorine? Well, it now accepted an electron from the sodium. It has now gained an electron. Its charge becomes negative. How do I know those charges are coming out? Well, sodium lost, so of course it's positive, because whenever you lose, you're like, yay! You're like, no, that doesn't make any sense. Whenever I lose, I get really sad. I don't get positive. Why is it getting positive when it's lost? What did it lose? It lost a negative thing. You go yay when you lose debt. Okay? You're like, yes, I'm out of debt. Okay? Because I lost my debt. That's a good thing. Okay? So it's not just recognizing losses and gains, but what are you losing and gaining? In these cases, you are losing and gaining an electron. And from that chapter 4, we know that the electron is what charge? Negative. So we have to keep that charge in mind when we go through and do these differences. Okay? We can look at ionic radii. What would you expect to happen to the sodium atom's size when it becomes positively charged? When it becomes positively charged, what did it do? It lost an electron. Well, the radius depended on what? The number of electrons. If I get rid of an electron, what happens to its size? It gets smaller. What happened to the chloride? So when we look at the atoms, the chloride is now really, really tiny in comparison to the sodium. The chloride now gains an electron, so what happens to it? It gets bigger. So we can look at those transitions and predict something about what happens to their radius. Notice there's a big string of numbers down there. Don't worry about it. Okay? The numbers are there just so that you can see those differences. You're not expected to be able to predict that it goes from 0.186 to 0.095. Don't do that. Okay? You're expected to predict that the number indeed got smaller. It did. That's it. Okay? Covalent bonds are a little bit trickier. Because when we look at a covalent bond, there's not a complete transfer of the electrons. They're sharing electrons. Okay? So what comes out of that is not looking at the radii for each individual atom, because that's no longer important. What we now look at is bond length. What is the distance between the nuclei? Well, if we're sharing electrons, the circle from the hydrogen has to overlap the circle from the chlorine. Those two must overlap. If they don't overlap, they can't share electrons, because that's what those shapes meant. That's where the electrons were. Which means what happens to the bond length if I compare it back to the radii of the atoms? The bond length must be smaller than the sum of the radii. Okay? So all we're saying is that that brings those atoms a little bit closer. That's it. How much closer? I don't care. It makes it closer. That's all you need. Okay? Bond energy is this exciting thing that isn't really exciting. And I don't think it's really worth, here, that's actually, it is super, super cool and important. Pause. So now let's re-record. What happens to the energy when we make a bond? Right? Everything in chemistry is trying to do what? Lower energy, higher energy. Lower energy. That is the goal, is to go lower in energy. What do you think happens when we make a bond? Should it go lower in energy or higher in energy than the starting atoms? It has to release that energy. Our bond has to be lower in energy than the atoms. Well, why might that be the case? Well, flip it. Make the bond higher in energy than the atoms. Our rule is that everything needs to go to lower energy. If everything goes to lower energy, do we exist if the bonds are higher in energy? Everything would want to be a single atom. There's no reason to make bonds because I would go up in energy. Do we exist? Let's not get all metaphysical nonsense on that. Okay? We know that we have at least our perception of the world where bonds exist, okay, or you're all figments of my imagination, okay, and vice versa, okay, in which case none of this matters. Okay. The bond is lower in energy. That means the atoms have to release energy. Okay. They're at a higher energy state, so to move down, that energy has to go somewhere. Okay. It is typically released as heat. If we flip it, okay, I want to now break that bond. Okay, well, to break that bond, to take it back to the atoms, I have to put heat in. Okay, I have to supply that energy to break those atoms apart. That's all we're talking about with bond energy. There's very particular specifics behind this, but that's all you really need for the sake of this. Which gets us to my favorite part, Lewis structures. These are the rules. Okay? Not these are a set of rules. These are the rules. Period. Bar none. Your textbook is awful. Okay? Other descriptions that I've seen out in the world are also awful. Okay? And it's not because you get the wrong answer when following other methods. Okay? That is not the issue. The issue is that you have no concept of why you followed those rules, okay, because those rules don't match the physical world, which means if you move into a more advanced chemistry class, I have to reteach you the real world and how it applies, and we waste a bunch of time. These are the reasons behind our rules. So number one, I need to know how many electrons go into the system. Most rules start out with that. That kind of makes sense. I need to know how many electrons are involved in making the molecule. Notice I only picked the valence electrons. What were the valence electrons? The outermost electrons. Okay? Does it make sense to use just the outermost electrons? What's the most likely thing to interact between you and another person? Your hand. You're talking to me, okay? Or, I don't know, your intestinal system. Your hand. Why? The hand is on the outside, okay? If you get close enough to each other, does the intestinal system potentially now get exposed to your other person, okay? And you're probably like, no, that never happens. Like, I don't know, farting next to your personal companion? Yeah, you eventually get deep enough where that interaction happens. So it is important, but you have to dig deep enough to get to that connection. Okay? If someone outright started farting in front of you, you might be like, yeah, I'm going to pass. Here, just let me go to the bathroom. Okay? Those are very personal, intimate things. We don't share those right away. Okay? So we start with our valence electrons, the outermost. Okay? So our highest energy. The next one, choose a central atom to act as a connector or bridge. Okay? This is usually the least electronegative. Okay? Because what are the most electronegative going to do? Well, what was electronegativity defined as? Grabbing all the electrons. If we put our most electronegative as the center atom, it now has to share with a bunch of other things. But what was the whole point of being electronegative? It doesn't share. So usually your least electronegative is the center atom. Okay? The exception being is it has to be able to bridge. So a hydrogen is a horrible center atom because hydrogen can only make one bond. It can't bridge two locations. Right? Rule 3, add electrons in pairs to the most electronegative. This is the one that stands out different from every other textbook, particularly general chemistry textbook I've ever seen. Okay? Is right here, rule 3. I want to put electrons into my structure. Where do I want to put those electrons? Around the most electronegative atom. I'm not saying center, I'm not saying outside, I'm saying the most electronegative. I don't care where it's located, I'm putting it on the most electronegative. Why? What does electronegativity mean? They want to grab electrons. So I'm going to start my drawing by putting as many electrons as I can on the atom that wants the most electrons. Period. Right? That's the whole point of this process. After that, I'll continue to add electrons to the rest of the atoms. Okay? Again, always going to the most electronegative in an individual set. How many electrons am I allowed to put around? 8. We follow something known as the octet rule. Why 8? Look at the second row. How many columns in the second row? On the periodic table, not on my screen. 8. Why do we call it an octet rule? Because there's 8 columns there. That's where it's coming from. It is sometimes also referred to as the noble rule. Why? How many electrons would our noble gases have in their highest energy shell?
They got everything.
They would have everything, which would be 8. Okay? Are there exceptions to the octet rule? Sort of. Okay? Really, there's only one big exception that you're responsible for. How many electrons go around hydrogen? 2. Why only 2 for hydrogen? In that first row, how many electrons fit? 2. That's why we stop at 2. Everything else gets 8. Okay? I will continue to add electrons until the total has been achieved. And this is a fun one too. The reason I did step 1 was to figure out how many electrons went in. Okay? So if I go through and say, well, this one doesn't have 8 electrons, so I'm going to put in 2 more. You can't do that if you've already achieved your total. So follow the total. The next part, convert pairs of electrons between atoms into lines. Only between atoms. Why? Because I'm trying to show a difference between what makes a bond and what is not a bond, which becomes relevant when we move into the Vesper models. Rule 6 is the next one that usually throws people for a loop, and this is where Rule 3 comes into play the most. Okay? If you've done everything up to this point correct, when you hit Rule 6, you're now set to be able to find your resonance structures. Okay? Otherwise, you have to know the answer. Okay? And this is where Lewis structure is challenging. You're like, I don't know how to do this one, so I'm going to look it up. You just looked at the answer. Of course you know the answer now. You can't just say, well, now I know how to do it. No, you know how to look up an answer. Rule 6 sets this up. If you have an atom that has not achieved its octet at this point, what you will have to do is move non-bonding pairs of electrons towards that atom. Notice what we're saying is place those electrons between the atoms. Because if I place the electrons between the atoms, I have now done what? Made another line. Now I have a reason behind multiple bonds. What if there was more than one source of electrons that could have moved? Well, that means there's more than one way to draw that structure. That is known as resonance, and as much as you may hate it, you have to draw all of those possible structures. Okay? At this stage, you have no way of differentiating what is good and what is bad of your resonance structures. So you're responsible for drawing all of them, bar none. Okay? Rule 7, assign formal charge. For CHM130, all you are responsible for doing is writing a bracket around your structure and putting a formal charge in the upper right-hand corner. Okay? That goes all the way back to 1. When you move up in chemistry, you're responsible for assigning that charge per atom. So if your structure has a -1, you have to say what atom has that -1. Okay? That is an extra step. You don't need to do that. I apologize. The video made you watch that. Okay? But now you know more. That's good. Okay? The next big summary that comes out of this is that we want to be able to interpret the shape of our structures. What you're seeing on this slide is all the shapes you are responsible for. So the instant you draw a structure, you then have to be able to interpret that structure according to this to tell me what the shape is. What the hell is trigonal planar? I don't know what trigonal planar looks like. I don't care. What you need to know is that trigonal planar means there are 3 bonding groups and 0 non-bonding groups. That's what it means. You have to memorize that shape comparison. Okay? If you move up 151, adds a whole nother fun little section after this, okay, known as trigonal bipyramidal and octahedral. You don't need to know that. You just need to know tetrahedral and up. Okay? So you now have all of the tools, so you're ready for the exam. Let's go ahead and put our notes away and we'll start the exam. I'm just kidding. Some people at least laughed. That was good. Looked like Ashton just about had a heart attack. All right, so we've got some examples. I don't remember which ones popped up in the video. Do you have questions about any of those 4? You look at them and you're like, I want to see that one. Second one, we'll start with that. So, NH4. Step 1. Total valence electrons. So nitrogen has how many valence? 5. Right? Because I don't think I talked about the shortcut on this. Let's look for a shortcut on finding valence. Because officially what happens is we look at 1s2, 2s2, 2p3, right? That's our electron configuration for nitrogen. Everybody agree with that? Yeah. So to get the 5, we'd say, well, highest energy would be those electrons. 2 plus 3 is 5. Right? That's a lot of work. I wonder if we had a tool that was handy that we could use and just look at, and it just tells us what that answer is, so we don't have to write out an electron configuration. I'm horrible writing electron configurations. You mean the periodic table has that information? Nitrogen. Which column? I won't quite accept 5. It says 15. If I subtract 10, that's 5, right? Yeah, why am I subtracting 10? The transition elements. Right? Don't like that. Okay, that's fine. Next one is Roman numeral V. I gotta know the Roman numerals? How many people know what V is? Okay, enough of you raise your hand to accept that. V is 5. Okay. Oxygen, VI, 6. How many valence electrons does oxygen have? Seriously? Fluorine, VII, 7. How many valence electrons does it have? 7. Okay, cool. Tellurium, that's got 52 electrons, so it's got to have way more valence electrons. Which column is it in? 6. How many valence electrons does tellurium have? 6. Seriously? Yes. Periodic table tells you the valence electrons. You have to be able to interpret that information. You have to know it's there. Right? Nitrogen has 5. What other elements do we have? Hydrogen. How many valence electrons does hydrogen have? 1. So we total that and I get 6. You'd be wrong. There's 4 hydrogens. Okay? That's what that 4 means. It applies to the hydrogen. So it's not just 1 hydrogen. There's 4 of them. So there'd be 4 electrons coming from our hydrogens. The next part that makes this one tricky is what else is happening in that formula. We see a positive charge in the upper right-hand corner. Okay? That is always where the charge will be specified. So I have to account for it because it is specified there. Remember, I'm counting the valence electrons. If it is positively charged, what happened? Okay. If I gained an electron, what charge would I become? Negative. So I can't add an electron because I'm positive. What did I do? I lost an electron. What's my total? 5 plus 4 minus 1. 8. Central atom, usually the least electronegative, but it must bridge. Hydrogen is the least electronegative between hydrogen and nitrogen, but hydrogen can't bridge, so not a center atom. That makes nitrogen our center atom. I will then place the hydrogens around it. Does it matter where? No. Okay, but as per the Lewis video, this theory came about by looking at how cubes interacted with each other, that we then simplified down to squares. So a good recommendation would be to draw a square around your center atom. When you place your hydrogens in, place them on the faces of that square. Okay. I now need to add electrons to the most electronegative. Which atom is the most electronegative, hydrogen or nitrogen? Nitrogen. So I will start adding electrons in pairs to the nitrogen. So there's 2, 4, 6, 8. Should I be putting more electrons in my drawing? No. Why not? Step 1 says my total needs to be 8. I'm there. I've got my 8 electrons. Convert pairs of electrons into lines. Okay? This is usually where students get irritated at me because I bust out an eraser, which is awesome if you have a whiteboard. And I will turn those into now lines connecting those atoms. Okay? Satisfy octet. Rule 6, everybody's favorite rule. How many electrons around this hydrogen? 2 electrons. But it says the octet rule. Don't I need 8? Hydrogen only has 2 electrons, period. It's in that first row. It can only hold 2 electrons. That hydrogen is okay. How about the next hydrogen? Next? And then 3, right?
Yep.
Just checking. 2 electrons. How many electrons around the nitrogen? 8 electrons. If I add up all of those numbers, isn't that more than 8? 2, 10, that would be 16. But I only have 8 electrons, right? Why is that not 16 electrons? They're sharing electrons. Because they're shared, they get counted for both the hydrogen and for the nitrogen. Okay? Does every atom have achieved its octet? Yes. Do I need to move electrons? No. Formal charge. This calculation you don't need to do, but what you do need to do is specify the formal charge. Was this structure charged? Well, go back up to your formula. Was there anything written in the upper right-hand corner? Yes. So do we need to specify a charge? Yes. It needs to get written in the upper right-hand corner. If we ignore all the electrons and put brackets, and I can say plus. Done. That is now the full Lewis structure. Scientists being lazy, me being no exception, you will often see me write this. That is not 7 plus, that is bracket plus. I don't want to draw the rest of the line in the other bracket. Both are perfectly acceptable. Does that answer your question, Lily?
So you just put one bracket, like the corner?
Yep. Does that answer your question? About this one or a different one? Okay, go ahead.
Nitrogen is the least electronegative.
Nitrogen is the most in this case, okay? Because it is closest to the upper right-hand corner. If we compare nitrogen to hydrogen, nitrogen is closer to the upper right-hand corner. That makes it more electronegative. What you're probably challenging is that it says the central atom should be the least electronegative. Remember, there are exceptions to that. It's a should be the least. Whatever that center atom is must be able to bridge. It has to be able to grab one atom and another atom, which means it needs to have at least 4 electrons around it. How many electrons can you put around a hydrogen? 2. It can't hold 4. Hydrogen cannot be the center atom in this case. Okay. That rule, too, is very open. So here we have a summary. The full directions a couple slides back actually showed all of those. Is that good now on that one?
I have a question on the oxygen and hydrogen negative. Got it.
Okay. Can I erase everything?
Yes.
If we switch to the oxygen and the hydrogen, valence, oxygen has 6. Hydrogen has 1. Charge. It's a -1 charge. So should I be writing -1 here? No, I need to be writing +1. To become negative, I had to accept an extra electron. That means my total comes out to be 8 electrons. Propagating this out real quickly. Oxygen, here's my box. Hydrogen, placing my electrons. I'll start placing them between the oxygen and the hydrogen first. Why place them there? I know they have to be bonded, so I'm going to start placing my first set of that 8 electrons in that location. I'll place the rest of the electrons around the oxygen. I've now placed my full 8 electrons. Anywhere I have a pair of electrons between atoms, I'll turn into a line. I now have my bond. Everything is satisfied as octet. The oxygen has 8 electrons around it. The hydrogen has 2 electrons. The last step, formal charge. There's that final answer. What's that?
You get rid of the dots.
You're converting the dots into a line.
So you don't.
So you shouldn't duplicate them. Okay. That is why I always go through and erase them.
Okay, so I get confused with the plus and the negative.
It is easy to get confused with the charge. It is easy. And the reason being is that what we're talking about moving is something that is negatively charged. Well, it's not that hard to deal with negative. Remember this conversation for every math class you go through, for every chemistry class, every biology class where you do a calculation that involves a minus sign. Okay? When you get the question wrong, go back and look at why. I can almost guarantee you 9 times out of 10, it's because you made that negative a positive. The negative sign is the bane of all human existence. Okay? It will ruin you in science. Watch out for it very carefully. Okay? It is a simple, easy thing to lose, and it destroys answers.
I'm just confused on why there's a positive charge.
There is not a positive charge. This goes back to it. You're like, well, the charge here says +1. That's not a charge. What is that?
It's an electron.
That's an electron. I'm saying I'm adding an electron. But what charge is an electron? Negative. Which means the charge for my molecule is negative. Okay? So it's recognizing what we're totaling. What we're totaling here is the number of electrons, not charge. It's the electrons contributed by the oxygen, the electrons contributed by the hydrogen, and the electrons contributed by the charge. For the charge to be negative, we have to add 1 electron. We're adding debt.
So are there always going to be 8? Or
No.
like, can we do one that's
Sure. Sorry, I just erased everything. Hopefully you were okay with me erasing everything, because it's not too late. Let's look at SO3. How many electrons does sulfur have? 6. Oxygen has? 6. How many oxygens? Okay. So 6 times 3 is 18, plus 6, 24. Which is the least electronegative that can bridge? Well, now I have oxygen and sulfur. Oxygen is the second most electronegative element, second only to fluorine, which means oxygen is the most electronegative in this pair, which means sulfur is the center. I'll draw my box to help me out. Oxygen, oxygen, oxygen. Did I have to pick those 3 faces? No, they could be on any one of those faces. It doesn't matter. Okay. I now want to place my electrons in, starting with oxygen. Which oxygen? Top, right, bottom? Doesn't matter because they're all equivalent. I'll start with the top one. Notice I'm still placing it to the sulfur first because I know I'm going to have a bond there, so I might as well start putting my electrons there first. How many electrons have I placed? 8. Can't place any more on oxygen, so I move on. How many electrons? 8. So I'm up to 16. There's another 8. What's my total? 24. Cool. I'm at my total electrons. I can't place any more electrons in. So any place I have a pair of electrons between atoms, I will turn into a line. So far, so good? You guys, Isaiah, Ashton, you guys good?
I'm just asking, but I'll figure it.
I would agree with yes.
It's all good.
Okay, just checking. You're fine to talk. I just wanted to make sure. Okay. So we now check octets. Does the oxygen have 8 electrons around it? Top one. Yes. Right oxygen. Bottom oxygen. Sulfur. How many electrons does the sulfur have around it? 6. Is that an octet? Octopus, 8 arms? No. Okay. It's a hextet. That doesn't count. It's got to be an octet. So I need more electrons on that sulfur. Okay. And whoever said, oh no, yeah, that's why I picked this one. Okay. What's the oh no? I now have to evaluate satisfying octets. I can move electrons, or moving pairs of electrons to satisfy the octet. And this is where the abbreviation here in our rules tends to trip people up. Because they say, well, you just move electrons. So I'm going to take these 2 electrons, I'm going to erase them because I'm going to move them to the sulfur. Does the sulfur have its octet? Yeah, but the oxygen doesn't. So it's not a question of just moving the electrons. Where do you move the electrons? Between the atoms. I now have a pair of electrons between the atoms. What does that mean? Don't go to double yet. What does that mean? I have a bond. I have an extra line. How many lines do I have there? 2. So now it is a double bond. We don't go into this saying make a double bond. We let the structure tell us that we need a double bond. Right? The method allows you to self-discover that. What the textbook suggests for its process ultimately means that you have to go in knowing the answer to get the answer. Of course you're going to get the answer. Then you know that. Okay? Let the structure tell you that you need multiple bonds. Okay? So before we make that more complicated, questions. Because you're giving me a little face, that's okay.
So does now it's offset?
So now do we have octet satisfied? Well, how much electrons are on the top oxygen? Well, 2, 3, 4, 5, 6, 7, 8. So it has 8. The other oxygens I didn't touch, so we won't count those. Now let's take a look at the sulfur. 2, 3, 4, 5, 6, 7, 8. Does the sulfur have its octet?
Yeah.
Yeah. Every atom has an octet. That's a valid structure. Good job.
Do you do anything
You don't seem very like excited about that. Well, like we have an answer. That's good. Be happy. You're like, I'm waiting for the shoe to drop. Yeah. Okay. What's the shoe that you're waiting for?
All possible
Okay, when we look at resonance, we have to evaluate, were there other pairs of electrons I could have moved? Could I have moved the very top oxygen's pair of electrons? Would that have resulted in a different drawing? Okay, so we need to evaluate, because this is where things get dicey, so we've got to make sure we're all on the same page. Right? That's what would have happened? Does everybody agree? What is the difference between those two structures?
The bonds are the same, though.
The bonds are the same. What's the difference? Because what looks different? Yes. The electrons. Okay? We're saying that those locations of those electrons are of critical importance. They're not. Okay? So those two structures are identical. Okay? So when we're talking about resonance, we have to draw structures that appear-ish different. Okay? In this case, those electron location differences are not different enough to count as different. These two should not be drawn as different structures for resonance.
Is resonance just there so you can like figure out, if you got something new or it's the same thing or?
Kind of. Okay? And you're looking at the application of resonance, which is kind of mind-blowing, so don't push that too far yet. Okay? Were there other electrons I could have used? Where? How about the oxygen on the right? Okay? What would the structure have looked like if I had moved those? Are those two structures, whoops, sorry, I missed that top one. Is that what you were telling me? Oh, no, I didn't miss it. It's actually drawn on mine, but I lost connection. Okay, there we go, right? Are those two structures now different? Okay. For people saying no, tell me why.
You just moved the electrons around, you still got 1, 2, 3, 4, 5, you still have octets.
All the octets are valid. Yes, I agree with that. Yes.
You're just moving the structure around a little bit. It's the same thing.
So here's the point. Someone's saying I'm moving the structure around a little bit. How would I move the structure around to get those two to be the same?
Just prove that there's only other ways you can
You'd have to
do
tear your double bond.
I would have to break other bonds. That doesn't count. That's breaking bonds. Can't do that.
Okay.
Are these different?
No.
Yes. Okay. They are different in that the location for the double bond has changed its location. Instead of being up, it is now to the side. These are now valid resonance structures. Yes, the octets must still all be satisfied. Okay, the whole point of resonance is saying I can draw another structure that is exactly the same but different.
What?
Yeah, I know. Okay. Is there another way I could have drawn this? What is that other way?
So when we're doing the test, do we have to show all these ways?
When you do the test, yes. If there is resonance, you have to show all resonance, yes. Are these structures different?
Yes.
Yes. Are these structures different?
Yeah.
If everyone accepts yes, we'll just leave it at that, because yes, I agree. Okay. One of the things that becomes tricky is that we have to lock our oxygen atoms down. Like if you filleted open a frog in biology or whatever, you pin pieces down. We're doing the same thing here. We're pinning those pieces down. Those atoms are now locked in those locations. They can't move, rotate, or spin. Okay? But what we are looking at is how can the electrons disperse through the structure. Right? And in this case, that pair of electrons appears to be dispersible throughout all of those bonds. Does that change the chemistry? Absolutely. I'm saying those electrons can exist in more space. Why is that important? Okay. I'm going to give you a 2 by 2 by 4 feet box. So you could theoretically fit into it, right? 2 by 2 by 4. And you think about your size, width, right? You got a little bit of space. Okay? You might have to hunker down a little bit, but you got a little bit of space. That is where you can now exist. How happy are you going to be? Not very. But now I say you can live in a 10 by 10 by 10. Do you get happier? Yeah. Now I say you can live in a 30 by 30 by 30. You get happier? Yeah. The more space we have, the happier we are because we have more freedom to move around. Same thing is happening with electrons. Because those electrons now can go to different locations, I have made them more happy. I have made them more stable. Okay. Said another way, can I erase all that? Here's...
So hang on, molecules that you can do resonance on are more stable?
Yes. Okay. So those are two circles. Okay? I'm going to make you stick your hand in one of those circles. Okay. To make this exciting, I'm going to add an electron. Okay. What do we know about electrons? They're charged. Okay. The outlet has electrons in it, right? And if we stuck a fork in there, that would hurt a lot. Okay? So if you touch that electron, you're in pain. Which circle do you stick your hand in?
Big one.
Why the big one?
You got more room to move around.
Okay. The odds that you hit the electron in the big one, much less so than if you try to stick your hand in the little one. What does that mean? That electron in the big one becomes less reactive because the odds of it encountering something to do a reaction are reduced. The more our electron can move, the more stable it becomes.
So the higher the electrons, the more reactive.
Sorry, say that again?
The higher the electrons, the more reactive.
I don't know what higher means.
Like the more electrons in there, then the more reactive that's going to be.
The higher the energy of the electrons, the more reactive. The more electrons I put in that space, the more reactive. Yep. Okay. All of that is true. Okay. Resonance allows us to see that those electrons can move. We have a larger circle. That's the point of resonance. Okay. Okay. I know we don't have a lot of time here, but this is officially the last slide I would look at if you've got questions about the exam. So this is exam relevant. Okay? Number one of your colleagues sent me answers and gave me permission to post their answers. That is posted to the discussion board. So I've posted their answers and my responses to the wrong ones. At no point have I ever said what the answer is. Period. Okay? So if you're interested in that, take a look at the discussion board. Okay. The next thing, you get a periodic table on the exam. Okay. It's on the back of the first page. What I would recommend you do is purge some information as soon as you're allowed to turn that page. Get that information down so when you encounter a question about electronegativity, about ionization energy, about atomic rays, about valence electrons, you know where to find it. It's not digging through your brain because your brain is a scary, scary place to be. Okay? And I'm not trying to be offensive. It just is. Okay? Just think back to the thoughts that you had from when you woke up to now. Through this lecture. Like if I heard all of those thoughts, would you be in trouble? Okay? Purge information. This slide shows that information as a purge. Okay?